Hello everyone, Disha Kansara here and my SEP ID is 600011980003 and today I'm going to explain the differentiator using op-amp and see the frequency and phase response of it. And so first of all, I like to explain the short introduction and the theory part of the differentiator. This is my the circuit diagram of differentiator with, and here the small uh, theory part of it. So it is an ideal lossless differentiator where an op-amp differentiator of or the differentiating amplifier is a circuit configuration which produce the output voltage amplitude that is proportional to the rate of change of amplitude input voltage. And in op-amp differentiating amplifier, it uses the capacitor in a series with the input voltage source. So for the DC input capacitor C1, it remains uncharged and behave like the open circuit. So the non-inverting input terminal of the op-amp is connected to the ground through the resistors RCOM, which the provide the input bias compensation, and the inverting input terminal is connected to the output through the negative feedback resistor RF. Thus, the circuit behaves like a voltage follower. When the input is positive going voltage, a current I follows the current where I follows the into the capacitor and is showing in a which shows in a figure. So since the current flowing into the op-amp internal circuit is zero, and effectively all the current flows through the resistors RF. The output voltage is V out is equal to minus I into RF. So this is the short theory part of the differentiator, and my calculation is this. So where I assume let FA is equal to 1 kilohertz, FB is I get the sorry, FE is my 10 kilohertz, and I assuming C1 is 10 nano farad. So my FA is 1 pi 1 upon 2 pi RF into C1. So my RF is equal to 1 upon 2 pi FA into C1, which approx is 16 kilohertz, and my FB is 1 upon 2 pi R1 C1, where R1 is 1 upon 2 pi FB C1, which approx 1.6 kilo ohms. And I assume the R1 into C1 is equal to RF into CF. So my CF is R1 into C1 by RF, which approx 1 nanofarad, and my RCOM is R1 parallel to RF, which is 1.5 kilo ohms. So this is my calculation of differentiator. So yeah, let perform on LT Spice the differentiator. So first of all, select the OP07 op-amp. I place it over here. Then I select the resistors where, yeah, I need 3 resistors here. Here and yeah, over here. Now I'm selecting the capacitor. One I place it here and one is place it here. So then I'm selecting the voltage source. One is connecting here and one is here. So yeah, and I also need the ground. Here I'm connecting a common ground. So yeah, this is all I placed the components. So now I'm connecting with the wire to all the components. Yeah, I sorry. Yeah, now I'm connecting all the components to open. Now I'm connecting the voltage source and to the common ground. Yeah, I connected all the components with the wires and now I'm labeling it. Yeah, I label it VCC. Yeah, now I'm going to change the name. This is my VEE. This is my V out. This is my VCC and this is my VEE. Yeah. Now this is my CF. This is my RF, let's say. This is my C1. This is my R1. And let's say this is my R2. Now I'm going to give all the values. Let's say CF is my 0.01 microfarad. My RF is 1.6K. My C1 is 0.1 microfarad. I move it here slightly. This is my 160. This is my, and let's say now I'm giving a value of this 15 volts, plus 15 volts and minus 15 volts. Yeah, and now I'm going to give this value, input value. So this is AC, let's say 1. And I'm run this. I select AC analysis. Here is my decade. Then it is my let's say decade is my 1000, this is 1, and this is let's say 100k. This is not decade, this is a linear. Oops. 100k. Yeah, so let's check the output. Now I added it. This is my decade only. I select run. So I run this, and yeah, so this is my output waveform of the differentiator when this uh, dark blue V out waveform, which is output, is a frequency response, and this dotted is my phase response of the differentiator. So let's check the another one of the sine wave. So I change the input here. I select the sine where offset is 0. My amplitude is 1 volt, let's say. This is my frequency is let's say 1k. Enter. And for this, added the simulate command where I select transient, where let's say my stop time is 10 milliseconds. Okay, and I'm run this. Yeah, so this is my sine of cosine, output of sine, output for the sine of a cosine, where my input is 1 volt and my output is also 1 volt. So let's check the another one. Yeah, I change this. I select here a pulse. I'm giving a -1 initial value. Then this is 1. This is my 1p. This is let's say T rise is my 0.5 ms. This is also my 0. Let's say 5 ms. T on time is 1, and T period is my let's say 1. Okay, I select this. Now I change my transient here. 10 milliseconds for my stop time, and it's 0 when let's say 1 micro maximum step time step. So I'm run this. In input I get the triangular wave, and output I get the square wave. So this is my second waveform for the differentiator, where my input is 1 volt, 2 volt peak to peak, and my output is around 0.64 volt. So this is my second waveform of the differentiator. And the another one where I change the time, let's say it's 1p, 0.5 and 1. I just slightly, yeah, and I change my transient time, let's say 20 milliseconds, and I run this. So yeah, this is my last waveform of the differentiator where I get the spikes of it, where my input is in a square wave and my output is in a spikes. So this is my output spike I got in a around 6.3 volts, and this is input is in 1 volt. So this is my differentiator, and uh, I also calculate the another frequency where my FA is 1 volt. I get the output 0.188, and my FA, no, yeah. So thank you.